This video demonstrates the pilot scenario 2.2, which showcases how ELECTRON detects and mitigates a false data injection attack that threatens to overload the electricity grid. As a charging station operator, Public Power Corporation, or PPC, utilizes the Open Charge Point Protocol, or OCPP, to administer multiple electric vehicle charging stations. Through this protocol, the operator can monitor and authorize the EV charging sessions, as well as to configure the EV charging stations. In terms of configuration, the operator can alter various parameters and configure the charging behavior of the EV charging stations. Amongst the available options, the operator can install charging profiles on the charging stations. The charging profiles indicate how much power an EV charging station is allowed to consume, either globally or within a specific time frame. The charging profiles can be used by the operator for optimizing energy management, but also as a safety measure, to prevent possible grid overloading, caused by multiple electric vehicles charging simultaneously. However, there are significant cybersecurity concerns to be considered with respect to OCPP. In particular, the most widely adopted version of the protocol, which is OCPP 1.6, does not enforce encryption or authentication on the OCPP messages. Hence, the OCPP infrastructure can be vulnerable to man-in-the-middle and false data injection attacks, allowing adversaries to modify OCPP messages on the fly. In this demo, we are focusing on a false data injection attack, in which the adversary edits the charging profiles transmitted from the operator to the EV charging station. In this attack, the adversary edits the charging profiles transmitted from the operator to the EV charging stations by increasing the limit value in the set charging profile.rec OCPP messages. As a result of this attack, the EV charging stations can draw more power than originally planned by the operator, thus risking a possible grid overloading, and possibly cause cascading effects to the wider electricity distribution grid. Considering the aforementioned, the goal of this scenario is to demonstrate how ELECTRON can detect and mitigate the OCPP charging profile manipulation attack. This is the architecture of the testbed employed by PPC for this scenario. The testbed replicates an EV charging station area, consisting of an EV charging station and the charging station management system. Moreover, we assume that the attacker gains unauthorized access to the network, while all components are interconnected through a hardware network switch that is managed through the OpenFlow 1.3 protocol. Before starting the demonstration, this is a summary of the steps that will be followed by the ELECTRON components in this scenario. Initially, the ELECTRON SDN controller and dashboard discovers the network topology, initializes the SDN switches, and scans the assets for vulnerabilities. Moreover, the ELECTRON Darcy component provides mitigation actions for assets and vulnerabilities by using manufacturer usage description files. Starting with the scenario flow, the ELECTRON FLIDPS analyzes the OCPP network traffic and utilizes AI-based models to detect potential threats or cyber attacks. Given a positive detection of a cyber attack, the FLIDPS generates security events, which are received by the ELECTRON Security Information and Event Management System, or CEM. The ELECTRON CEM correlates similar security events coming from the FLIDPS, and generates security alerts. Next, the ELECTRON Army component receives the security alert from the ELECTRON CEM. By utilizing information about the current topology assets from the SDN controller, and the possible mitigation actions coming from Darcy, the ELECTRON Army conducts risk assessment, and generates a risk assessment report. The risk assessment reports includes the identified threats, as well as mitigation actions that can be applied for them. Finally, the ELECTRON Nero component receives the risk assessment report, and decides on the best course of action. Depending on the decisions, Nero interacts with the SDN controller and programs the network switches accordingly, in order to mitigate the charging profile manipulation attack. Starting with the demonstration, this is the web-based user interface of the SDN controller and dashboard component. In the home page, we can see the SDN switches that are currently online. By clicking on an SDN switch, we can see more information, including the associated SDN controllers, the available switch ports and relevant statistics about them, and statistics about the available open flow tables on the switch. Next, in the flows page, we can inspect the flow entries installed on each SDN switch. Table 0 is the entry point for all network traffic, and Table 100 is where the flows of the SDN controller are installed. Following a reactive flow installation approach, the SDN controller has installed automatically the flows that allow normal communication between the network hosts. The flow control page allows the network administrator to manually create and insert new flows. Next, the current topology is visualized in the topology map, including all hosts discovered by the SDN controller. More details about each host can be viewed in the asset inventory. The asset inventory agent has already been executed, and has populated the asset inventory with more information about each asset. For example, we now open the details of the charging station management system. We see some basic information, like the operating system, and the MUD URL corresponding to the asset. The asset is hosted on a Raspberry Pi single-board computer, therefore, the corresponding MUD URL has been assigned manually by the network administrator. Some network details are also present, including IP and MAC addresses. On the right side, the network services currently running on the asset are depicted, which have been discovered automatically by the asset inventory agent. For each service, some vulnerabilities have also been discovered automatically. We can also see more details about the EV charging station. The network administrator has manually assigned the asset name, which is the device model, while the operating system has been discovered automatically by the asset inventory agent. Network information is also present, including also a host name. Finally, only an SSH network service has been discovered, which is used exclusively for remote administration of the device. Some vulnerabilities have also been discovered for this SSH service. Now we move on to the FLIDPS component. We start the execution of the component, which analyzes the network traffic to detect potential cyber attacks. While the attack is ongoing, we notice that the FLIDPS detects the charging profile manipulation attack and generates security events. Moving on to the dashboard of the ELECTRON CM, we can see the security alerts created by the CM. The security alert is formed after correlating multiple similar security events. Some important information are the source and destination IP addresses, as well as the overall risk value of the alert, calculated by the CM. This view of the Army dashboard showcases the runtime operation of the ELECTRON framework. When a new security alert is reported by the ELECTRON CM, a new notification is triggered to the Army dashboard. Subsequently, this notification results in a new risk assessment to calculate the updated risk posture of the monitored infrastructure. This risk assessment allows the DASI component to provide a set of mitigation actions based on the risks of each node in the topology. These mitigations refer either to a specific vulnerability or the correct configuration of an asset. If we look closer to a mitigation policy, we can see the detailed medium-level security policy language, or MSPL structure, expressing the exact steps that should be applied by the SDN controller. By inspecting the notification list, we can verify that indeed, the first notification refers to the false data injection attack, reported by the ELECTRON CM, as well as the fact that this triggers a new risk assessment. By having a closer look at the risk assessment results, we can see that the asset percentage is marked with the risk of very high. In fact, by inspecting the risk heat map, we can see that there is one risk that is identified with the threat probability of very high, and vulnerability impact of very high as well. This risk refers to the false data injection incident, reported by the ELECTRON CM. Since it is not possible to identify the exact vulnerability that led to this security incident, we classify the vulnerability as unknown, in order to state that this threat may stem from a zero-day vulnerability. Finally, by looking at the risk graph, we can now see that there are neighboring assets in the topology, where different attack paths may allow an adversary to pivot from one entry point asset and penetrate the topology. This showcases the need for an attack path assessment calculation supported by ARMI. Moving on to the Electron Nero component, we now see the terminal output of Nero. The logs of Nero indicate that a new risk assessment report has been received from ARMI. Therefore, a new mitigation process is triggered. The risk level value, contained in each entry of the risk assessment report, is checked against a predefined threshold. If the threshold is reached, then Nero applies the corresponding mitigation action. The asset with ID 1379 has an alarm with a very high risk level, which exceeds the accepted threshold. Therefore, the corresponding mitigation action is activated. The mitigation action for blocking the involved IP addresses is activated, and the respective command is issued by Nero to the SDN controller, in order to apply the mitigation action. Finally, in the SDN controller and dashboard, we can see the result of the mitigation action instructed by Nero. In particular, we can see in the flow table of the SDN switch that a new flow entry has been inserted by Nero. The new flow entry has a greater priority of 30,000, in order to override the normal communication flows. The new flow instructs the SDN switch to drop the packets of the compromised OCPP session between the EV charging station and the charging station management system, thus preventing further transmission of malformed packets.